Good afternoon, everyone. Welcome to join the colloquium today. And today we have a really great pleasure to hear about the most exciting news about the discovery of the black hole in our own Milky Way, in our backyard. And today's talk will be given by two of our very own postdoctoral members. And the first person will give the talk is by Cristina Romero-Canizales. And Cristina got a PhD from University of Granada in Spain in 2011. And later he worked in Finland, Chile as a postdoc research fellow. And also work at the University of in Chile, and also been involved in some of the transit events like a supernova and the tidal destruction event. And he joined this GLT and VLBI at the ASIAA in 2020, and he is also a member of EHT since 2020. And now she serves as a junior science counsel of these collaborations. Another speaker is Britt, and Britt got the master's degree from University of Illinois in 2014, and later got his PhD at the University of Waterloo in Canada in 2020. And now he is a postdoc fellow at the ASIAA, and also has been a EHT member since 2016. And today, both of them will talk about, each of them will talk about 25 minutes about the exciting discovery of our own black hole. So I just, let's welcome their talk, and I'll leave the stage to Cristina. So Cristina, please present.
Thank you, Ken, and thank you everyone for joining. So today we are going to present the first results of the Event Horizon Telescope towards Sagittarius A star. Britt and I, on behalf of all the GLT EHT collaboration. So this is a very large collaboration. Actually, there are like 80 institutes around the world. And among the stakeholders, we have ASIAA. So this is the outlook of presentation. We are going to make a summary of the papers that were published on May 12th by the EHT. And you can find in that link there and the QR code, you can find a link to all the papers. So we are going to start first with a quick summary of black holes. Black holes are a mathematical consequence of general relativity, and they can be described by two properties, which are their mass and their spin, according to the Kerr metric. We have empirical evidence of these objects by the study of X-ray binary orbits, and also the merging of stellar mass black holes. But really, when the nature of quasars was unveiled, that they are not stars, but rather they are very luminous objects, very massive in the center of galaxies, when many people got very excited about them. So what we know is that supermassive black holes are mostly in the center of nearly every galaxy, and they play a key role in their evolution. However, we don't know exactly the details of how they variate and how they grow. And so here we have this artist impression that it just comes to mind when we think of a black hole that it's accreting material. It will have not only radiative, but also some kinematic feedback and will interact with the medium. But if we take a closer look to what's happening in the innermost region, we will see something like this. So here we have a black hole with event horizon of the size of 2 Schwarzschild radii. And this will cause a very strong gravitational field. And so what will make is that the light that is coming from behind, it will just go around it, it will be bent. And when it arrives to us, just to a distance, we will see a magnified vision of that event horizon, and it will have a size larger than that. So we should be able, if we observe in that region, we should be able to see a very bright ring, larger than the event horizon, and it should be surrounded by this. There should be this very bright ring, and then in the center we should be able to see this shadow or brightness depression. And this is basically what the EHT can do. Can detect directly these gravitational signatures of a black hole. And just for you to know about the black holes that we have nearby. So the closest one, of course, is Sagittarius A star. It's only 8 kiloparsecs away from Earth. And these sizes are the apparent sizes, so they already take into account the distances. So if we compare it with M87, which was published 3 years ago by the EHT, Sag A star even has a larger shadow size that we should be able to detect. And we have, for comparison, these 2 other galaxies, which also have a supermassive black hole candidate. But we see that the expected shadow size is much smaller. So really, these 2 are the primary targets for the EHT. Another thing which is attractive from Sag A is not only it's our black hole, our supermassive black hole, but it's also in a quiescent state, as this is the most common feature in black holes around the universe. M87 has a very prominent jet, which we don't see in Sag A. The other thing is that it has very strong variability. So, of course, these are apparent sizes, but the actual size, of course, of M87 is much bigger than Sag A. And so what happens is that light that orbits around the black hole, in the case of Sag A, it will complete an orbit much more quickly in terms of minutes, whereas for M87, it will take days or even months to complete an orbit. So that tells us that we can expect very short dynamical scales in Sag A, and because of that, we can expect very strong variability near the black hole. So Sag A has been studied by many throughout time and in different wavelengths, and perhaps the most famous discovery recent that was made was that by studying in the near infrared the orbit of a cluster of stars, it was found that the gravitational potential is dominated by a very compact supermassive object. And so that's the first indication we have that there is truly a supermassive black hole in our galaxy. But still a candidate, because we cannot see. We only see the effects, but we cannot see the black hole itself. We also know that Sag A is not very luminous and also has very small accreting power compared to other sources. But the important thing here is that because it's so nearby, we are able to distinguish the black hole signatures more easily if we observe at low frequency, high frequency with the EHT. So it was actually one of the motivations to form the EHT. And so this is the campaign of the observations that we are going to present now. These observations were made in 2017. And this is the Earth as seen from Sag A, from the position of Sag A. So we had 8 participating telescopes at 6 different locations. So we can see that in 2 of these locations, we have collocated instruments. In Chile, we have APEX and ALMA, and in Hawaii, we have the SMA and JCMT. So this was the array of the EHT at that time that observed Sgr A. So for those who don't know, VLBI, or very long baseline interferometry, is a very, it's not new. It's not a new technique. It's been there for decades. And so more or less how it works is that if you have 2 telescopes apart from each other, they are receiving the same information from a source in the sky. And that information, it's digitized. It will have a timestamp corresponding to the time at which the emission was received. That emission will be recorded, and then it will be shipped to places where they can put the signals together. So that's called correlation. So what this does is it will try to find the interference fringes that will basically align the signals. And after that, the data will be ready to be processed. We have 2 different pipelines for doing that. And first stages have to do with the stabilization of the signal, then conversion of the amplitude to physical units, then removing offsets between right and left circular polarizations, and then further adjustments of the amplitude gains from every telescope by using those information from the collocated telescopes, which form what we call intra-site baselines. So the vectors between two telescopes projected on the sky is what we call baseline. And so this is the campaign of observations in 2017. It lasted 5 days, consisted of 5 days observed with the EHT. And then it was also observed by a number of other world-leading telescopes at different wavelengths. And so the idea is that if there is some variability occurring at very close to the event horizon, we would be able to match it with variability that we can see at other frequencies and also at different spatial scales. So that was the motivation. So now we go to how the data looks like. So I mentioned we have 8 telescopes from 6 locations. We have 5 nights, but among those nights, there was one which had like the best coverage, which is, this is called the UV plane. I mentioned already before about the contribution from each pair of telescopes will give us 1 point in this plane. And as the Earth rotates, it will describe an arc. So this is the information that we have. Of course, it's not completely sampled, but this is what we can do with this time and this amount of telescopes. So we have chosen, or we are going to focus now on the April 7th day of data, which gives the best coverage, and it's also the least variable. So for future studies, you will see that on April 11th, there was a flare, and it's now being studied in detail. So to the right, we have the plot of the calibrated amplitudes versus the baseline length in terms of wavelength. So these are gigalambdas. And this is how the data looks like. It's color-coded by pairs of telescopes. And here, just for guidance to your eye, we have put the corresponding of a Fourier transform of a ring convolved with a Gaussian. And so what we should be able to see is that there are 2 moves in the data. So this is just for guiding. It's not the final result. And so the amplitude of this second bump will determine the width of the ring that was used here. So already the data, the calibrated data shows that there has to be some signature of a ring. So even I said that this data was the least variable, but still if we look at the light curves of ALMA and SMA, they actually show some variability. And this is up to 13% of the total flux. So it varies a little, but it's still something that we have to take into account when we make our images. So this is just one of the challenges that we had to deal with. But then, of course, there was another challenge I mentioned. There's variability, but there's also sort of scattering. So in terms of variability, if we compare with what we obtained with M87, we can think of two dogs. One is a big dog representing M87, is basically not moving. And then we have another dog, smaller one, which is chasing its tail, so it's moving very fast. And then on top of that, we have a screen that it's distorting a bit the light that comes from it. So this was the challenge that we faced when imaging Sgr A. So the other challenge was, as I said, that screen that was in front of the dog. It's the interstellar scattering. So we have this foreground electron density that is fluctuating between us and the galactic center. And it can be represented by this kernel, which has a size of about 20 microarc seconds. So that's smaller to the size that we are actually expecting to see the image of Sgr A. But it's still something we have to take into account. So again, here we have the calibrated amplitudes in terms of the baseline length. And these are the projections of that scattering, diffractive scattering that we can see above. So there are actually two effects of the scattering. One is that the light will be bent. It will appear as coming from a broader place, so that it will cause an angular broadening. And the other effect is refractive, like when you change from one media to the other, the light will be refracted. So, and this will cause some spurious substructure. So to mitigate these two components, we went through two processes. One was the blurring, which is basically divided by the kernel of the scattering. And the other one was to take into account for the spurious substructure, we added a floor noise to the data. And yeah, so this is basically the process we did. But then for the imaging, it was challenging still. And what we did was to use three different methodologies using 4 different pipelines. So clean is the most common, is the most traditional methodology, and we apply it through software called diffmap. And this basically, what it does, it relies on the inverse of the Fourier transform to recover the true brightness distribution in the sky. And the other two methods are newer. They basically rely on the modeling. So one is called regularized maximum likelihood, and the other one is called Bayesian approach. So regularized maximum likelihood, it's an optimization problem. Basically, it reconstructs the image by maximaxing some likelihood function defined by some image parametrization. And the Bayesian approach is basically, it models the image at the same time that gives us an error image. So we use all these methods for the imaging. But then, of course, because there could be some biases in the choices we make when using these methods, we also tested using what we call synthetic, a suite of synthetic data. And this is basically to check if the morphology, what's the morphology we are seeing, if it's a ring, if it's asymmetric or symmetric, or if it has a component which is rotating, as in the case of this second column. And the other one was to assess the brightness depression that we might see in the ring, in the middle of the ring. So in total, we have 4 models which consider ring structure. which are the three to the left and the rightmost one, GRMHD, which also includes some physical quantities. And then the other are non-ring models. So this was what we did to be able to test the methodologies and the reconstruction. So what we did was to make a survey conducted in exploring different parameters from about 10 to the 3 to 10 to the 5 parameters that we explored. And then from making images with all our methods using all these models, we realized we can extract some top set of parameters that reconstruct accurately the images. So these are the so-called truth images, which are like a time average of the synthetic movies. And we can see that the different pipelines that we use, DIFMAP, EHD imaging, Smiley, and FEMIS, they are all able to recover the structures from the synthetic data set. So having determined those top set parameters, we created thousands of images that can actually recover the aspects from the data, such as the amplitudes and the position of the nodes. So all of these different images actually fit the data, and they can be further categorized in terms of whether they are ring-like or non-ring-like. And for those which are ring-like, where is the position of the brightest component? So one of the challenges was that even though we were initially recovering ring structures, the azimuthal brightness was not very well determined. So having this survey allows to make these images that later are clustered and later are being averaged to give us representative images from every cluster. So as I mentioned, we have 3 which are ring-like and 1 which is non-ring. And so considering all the amount of images, about 95% of the top set images are actually reconstructing rings. And the diameter and thickness are consistent, but as I mentioned, the azimuthal structure is not very well constrained. So when we average all of this together, we arrive to the representative image of Sagittarius star, which I remind you, it's an average over reconstruction methodologies and also reconstruction morphologies in time. But the important thing to notice here is that we have for the first time direct evidence that there is a supermassive black hole with a shadow size of 50 microarc seconds. And this is something that the Nobel Prize winners in 2020, they couldn't determine this. The Nobel Prize was for discovering a supermassive compact object in the center of the galaxy. So this is something that the EHD has achieved. So 2 things that were playing in our favor when making the image is that we got a slightly better coverage than for M87 because we also have added baselines with the South Pole telescope. Here also we don't have any contribution from extended depth, so the compact flux is actually larger. And the 2 things that I mentioned that were challenging was variability, that Britt is going to talk more about that, and the interstellar scattering. But nevertheless, this is the first Sagittarius image. Now, Britt is going to tell you about what we can learn from these images.
Can everybody see my slides?
Yes.
Great. Okay, so like Cristina mentioned, variability in Sagittarius A is actually one of the most challenging aspects of conducting our analyses. And like Christina mentioned, there's a long history of observational evidence that Sagittarius A should be variable on very short timescales, at essentially all observation frequencies. And simultaneously with the EHT observations, there were also sub-campaigns with the connected array elements that were part of the EHT, that is ALMA and SMA, and they were able to sort of look at the light curves that they were able to produce and sort of get a handle on what the sort of global fluctuations would look like for Sagittarius A at the same time as our campaign. And so you can see on, for example, April 6th and April 7th, there's sort of mild variability across the entire night. And on April 11th, which is the last day, the Chandra Observatory detected an X-ray flare essentially right before we started observing. And so you can see sort of evidence that there's sort of substantially more variability on that day on our connected element arrays. And so this is why we sort of focused on the first 2 days in our analysis, because we wanted to make sure that our methodologies and techniques could recover important information on more, simpler data sets. And we're saving, one of the more exciting data sets for later, once we have a better handle on what we should expect. And of course, along with observational indications of variability, there's also the theoretical prediction that Sagittarius A should be variable. Again, like Cristina mentioned, the shortest timescale in Sagittarius A is about 20 seconds, and orbital timescale should happen on the order of minutes to half an hour. And so we expect a significant amount of variation over an entire night, and this sort of means we have to rethink our aperture synthesis technique, which is to say we can't wait for the Earth to rotate and then average all those data points in the UV plane, assuming that those will give us the same image. We have to sort of accumulate our UV points and with the assumption that each sample represents a sort of independent image on the sky, even if they might have similar behavior. So what we did is we took a look at our large library of GRMHD simulations to sort of get a handle on what we might expect the visibility to be, or the variability to look like in terms of spatial and temporal structure. And we came up with this idea to sort of separate these GRMHD simulations into a sort of collected average image plus some variability residuals. And in this case, we can sort of separate out all the variability and sort of characterize that separately from what we might think of as the average. And it turns out throughout our entire library of GRMHD simulations, they all exhibit a sort of universal behavior, which is to say they all exhibit sort of a broken power law behavior in the Fourier transform. And so here on this right-hand side, this is a plot of sort of different amounts of variance and sort of noise in the data set. So in green, you can see what we expect to be the systematic uncertainty in our data that comes from telescope uncertainties. The purple shaded region represents what we expect the contribution to be from the refractive scattering screen. And then the purple lines represent individual realizations of that scattering screen, which in principle evolve over time. And then in red, we have what the power spectrum for the GRMHD simulations look like for different amounts of averaging. And so if we average a GRMHD simulation over a minute, we get this very low amount of variance. But if we average over an entire night, which is what we're doing with the EHT, you can see that the variability variance is actually dominating all the other sources of noise in sort of variability and variance in our system. And so this means that we can try to model this variance as sort of a noise parameter along with all the other sources of noise in our system. And we model this variability variance as a broken power law as informed by the GRMHD simulation. So we have a amplitude and a short and long baseline power law index, as well as a break at some characteristic point in UV space. And of course, we're going to add this to all of our other sources of noise to create a sort of model for our variability noise, and essentially try to fit this at the same time that we sort of try to extract an average image. And you can see sort of a larger discussion of this in one of the official papers associated with the Sagittarius A publications, which are all on the same page in the focus issue. So when we actually apply this to the real Sagittarius A data and take a look at what the model says, what the model recovers, we can see that here in a very similar plot, we sort of bin up all our data points in UV space into small 1 gigalambda chunks. That's represented by these black points. And you can see that between about 2 and 6 gigalambda, the variability variance is significantly larger than the other sources of noise. In this case, these gray points represent the thermal noise in our instrument. The purple, again, represents what we expect from the refractive scattering screen. And you can see that these black points, which are the variability noise, are substantially larger than that. Beyond about 6 gigalambda, the variability noise becomes comparable with the refractive scattering, and so we're not really able to disentangle those two effects. But otherwise, we're able to show that as long as you subtract off the global variation from the light curve, Sagittarius A is, relatively well described by this broken power law model. And so now we have a characterization of this variability. We have two different approaches to actually going about our imaging and modeling efforts. One is to conduct a snapshot modeling approach where we divide up our data into short time segments where we expect the source to be static. In this case, we chop it up into 2-minute time segments. And then we add up all these independent fits together to try to get final physically relevant parameters. And then we also have a full track approach, which essentially treats all the data all at once and fits an average source model along with a parameterized variability noise like I described before. In this case, we're sort of fitting both things simultaneously. So now that we have a way to sort of describe our variability and we have our two methodologies to investigate the model parameters, let's sort of talk about what sort of model we want to use to investigate properties of Sagittarius A. And we can take a look at the visibility domain, just to get an idea of what's going on here. And we can see that there are sort of, it decays at very short baselines, and then there's sort of a second hump around 4.5, maybe 5 gigalambda, and then it drops down again and has a second peak at around 8 gigalambda. And so this is pretty indicative of, for example, a blurry annulus. In this case, this geometric model here is represented in this plot as this gray line to sort of guide the eye. And these sort of important features in the visibility domain, that is the location of these two nulls where the visibilities drop off, give us a strong prior on what the ring diameter should be. In this case, the first minimum and the second minimum line up to give us something that should live around 50-ish micro arcseconds. And then the height and ratio of the height of the two maxima, after, of course, the initial zero baselines, gives us some indication of how deep the central depression should be, as well as sort of an understanding of how wide the annulus should be as well. And so from this, we can sort of construct our sort of fiducial geometric model, which will be a blurry ring with some level of brightness asymmetry azimuthally distributed around the ring, along with a some amount of dim central depression. And when we take this geometric model and compare it with other geometric models that might fit the data, like, for example, a double point source or some other geometric models that can recover a multiple null structure in the visibilities, we see that across the board, ring-like models provide better fits to the actual Sagittarius A data than any other geometric model for the same level of model complexity. And so here we just plot versus a log of the Bayesian evidence, sort of different geometric model fits to the data. And here at the very top end, you can see that ring-like models always do better than non-ring models for the same level of complexity. And so we'll use this geometric model with the two sort of mitigation strategies we talked about before. So in snapshot modeling, like I said, we split the data up into 2-minute snapshots and fit our fiducial geometric model to those snapshots, and then aggregate all those fits together at the end to get sort of an average distribution over the course of the night. And with full track modeling, we simultaneously reconstruct the variability noise parameter that we talked about as additive to all the other noise parameters. And we also model, of course, the average structure itself at the same time. And when we do this full track modeling, we're also adding both days that we consider together, primarily because the more data and the longer time span you give the full track modeling code, the more appropriate this variability noise prescription becomes. If you only look at one night, you're essentially only getting one sample of the variability noise at a time. But if you add multiple nights, you're essentially adding statistical value to the data set. So when we put this all together and compare against all the methods, both imaging and geometric models, we find that the image morphology is well described by a 52 microarcsecond ring that has a thickness about 30 to 50% of the ring diameter. Of course, the geometric models and image reconstruction models also explore a few other parameters like the depth of the central depression and the distribution of the brightness asymmetry, but those are a little bit less well constrained in our data, primarily because we don't quite yet have the coverage and sensitivity of their instruments to be able to distinguish these sort of more subtle parameters. Primarily because as we're doing the fitting, like I said, Sagittarius A varies wildly from minute to minute, and we need more and more data on longer timescales to be able to settle down on an average image. But we are pretty happy, though, that the diameter seems to be pretty consistent across all methods, and as well as the width. And these are going to be important in talking about interpreting these relative to GRMHD simulations and later to theories of gravity. And speaking of theories of gravity, what we can do is, now that we have the diameter, we can sort of calibrate that against sort of known quantities in our GRMHD simulation library to sort of give us an idea of the gravitational angular diameter. In this case, it turns out to be about a little bit under 5 microarcseconds. So that's this parameter here, theta g, which is just g over c cubed times the mass to distance ratio. Comparing that against all the stellar orbits measurements, that is from Keck and VLTI, you can see that all of our reconstruction methodologies are consistent with the existing mass estimates and gravitational angular diameter estimates from the other methods, which is good. I think it's a good reconstruction of existing procedures. And back to the GRMHD library, one of the great things about the Event Horizon Telescope is that we don't just make good images, but we also really want to try to say something about the region around black holes and see if we can, by using the images, if we can constrain any of our theories for the motion of material nearby black holes. And so we have this very large library that consists of petabytes of simulation images, spectral energy densities, and fluid dumps from a bunch of different GMHD simulations that are primarily divided into either magnetically arrested disk models or standard and normal evolution models. The difference here is MAD models have very large magnetic fluxes at the horizon, whereas sane models have very low magnetic fluxes. And of course, these span a sort of coarse grid of angular momentum spin parameters, as well as inclination towards the line of sight. And they also span a coarse grid in electron temperature functions, because the GRMHD simulations don't have the resolution to be able to model the kinetic motion of particles, that is, we can't actually, from first principles, determine the connection between the ion distributions and the electron distributions. We have to paint that in sort of by hand. And so in this case, we sort of heat up the electrons sort of by some factor, either 110 or 160, hotter than the ions, to sort of simulate a different connection between the two. We also have a bunch of exploratory models in addition to our standard set that explore non-thermal electron distributions, tilted disk models, as well as models that are fed at the boundary box from a sort of simulation of the stellar winds around Sagittarius star. Make sure this loops. All of these models are then fit against various constraints that we want to investigate. So in this case, we have a set of EHT constraints where we can compare our GRMHD models against, for example, the size of the image at 230 gigahertz. We can compare against the sort of morphology of the visibility amplitudes, as well as do a coarse comparison with respect to the diameter, width, and asymmetry of our geometric model system. We also have constraints at other frequencies, namely 86 gigahertz and infrared and X-ray. And we also have what turns out to be a very important constraint, is a comparison of the overall light curve as well as the variability at 4 gigalambda. And it turns out, as you can see in this movie, the models that pass all these constraints are zero. No model in our library, and even in the exploratory library, passes all constraints simultaneously. A few models survive the EHT and multi-wavelength constraints, but it turns out the variability constraints are almost orthogonal to those and lead to sort of cutting out everything else. And so here's sort of pie charts demonstrating that, where radially we have different models in terms of their electron distribution. On the top, we have the standard and normal evolution models. On the bottom, the magnetically arrested models. And in sort of angular distance, we have the inclinations. And if a set of simulations fail all the constraints, they're red. If some of the simulation sets pass, they're yellow. And if all of them pass the constraints, they're green. And so for the EHT, you have this sort of small region of magnetically arrested models that generally pass most constraints, but a lot of those are knocked out by the multi-wavelength constraints. And if you combine those, you have sort of a small region where some models pass all those constraints, but it is unfortunately orthogonal to the variability constraints, which is, I guess, interesting for us. You know, we didn't necessarily expect that all of our models would pass, but we certainly expected to do a little bit better. Generally, though, this is sort of not the end of the world, but all of the GRMHD models are generally more variable than Sagittarius star, and typically MAD models are more variable than sane. And there's maybe a couple reasons to expect this. In these GRMHD models, we model the accreting plasma as an ideal fluid, which is not necessarily accurate. They should be a collisionless fluid. And so there's maybe some room to sort of fudge that a little bit in the simulations in the future. And we can also make improvements by adding explicit conductivity to the simulations, as well as a better model for radiative cooling. And hopefully these should be able to smooth out some of the rapid variations that we see in a lot of our simulations. Putting aside the variability, though, we have sort of a best bet region in the model parameter space that is described by a high magnetic flux, a prograde spin that's oriented more towards our line of sight here at Earth, and with a relatively high electron temperature. And models that are disfavored have electron temperatures more in line with those of the ions that are edge-on and have spins, negative spins. The other thing we want to test with the EHT is not just sort of the astrophysical parameters around black holes, but the black holes themselves. It'd be great to be able to test GR with the EHT. And to do that, we're really testing the no-hair theorem, which is to say we're testing the Kerr metric. So all black holes that satisfy GR should be characterized by the mass, spin, or charge. And for astrophysical black holes, that simplifies down to test of the Kerr metric, which are black holes that are described by their mass and their spin, since we expect a lot of these black holes to be charge neutral. And so thus, any deviation from the Kerr metric is by necessity a violation of the no-hair theorem, which would then be a violation of GR. And so to check the Kerr metric, what we can do is we can observe the shadow size and compare that with the prediction that we get from the Kerr metric. And then depending on the spin, that shadow size should be anywhere from 4.2 to 5.2 theta g. And hopefully, if you remember what we showed before, we do in fact live in this region. But then we can also compare that with the other mass priors from the different stellar orbits results. And so when we do that, we see that, of course, all the different methods are generally consistent or explicitly consistent with the priors from either the Keck observations or the VLTI observations. And it seems like Sagittarius A is very much consistent with a Kerr black hole and a mass of 4 million solar masses. It turns out this diameter, of course, is related to sort of an unknown scaling factor that's related to our astrophysical uncertainties. All the emission and photons coming from the plasma around the photon ring can, in some sense, pass in front of the photon ring and modify the shape and sort of distribution of the light around the ring in ways that are not exactly related to just gravitational effects. And so that's what this alpha parameter is. And then we can compare it against what we'd expect from a non-spinning Schwarzschild black hole. And that's where this delta factor comes in. It turns out Schwarzschild black holes provide sort of the maximal size of the photon ring and the event horizon. And so comparing against that will let us sort of make estimates for how well we're doing against GR. And so we can compare with a bunch of other different metrics. Of course, it's maybe impossible to compare every non-GR metric out there because it seems like there's every day someone is coming up with a new one. But there's a lot of sort of metrics that are relatively mature in the literature. And we can test that with the fractional deviation range we get from the stellar orbits measurements. And we can see that while a lot of non-GR solutions are relatively challenging to rule out because they predict only modest deviations from a Kerr black hole, some of the spinning metrics we are able to rule out since they would provide deviations from a Kerr shadow that are larger than what we get with the EHT. And so as sort of a summary for the GR constraints, we can show that Sagittarius A's apparent diameter is consistent with the Kerr metric by at least 15%. And then measurements of the shadow depth and the infrared flux provide very compelling evidence for the existence of an event horizon in both Sagittarius A and M87, combined with estimates of the deviations from GR in other black hole experiments, namely LIGO and other stellar mass black hole experiments. GR provides an extremely strong prior for describing black holes across 10 orders of magnitude in mass, which is perhaps one of the most astounding sort of results, I think, in astrophysics. I mean, this is a tremendous range in parameter space, and GR does a great job describing all of it. And of course, the association of the ring-like emission we see at the EHT scales with a gravitational feature constrains all of that 4 million solar masses into a region that's 1,000 times smaller than that determined by the stellar orbits observations. And so we're able to really constrain all of that gravitational stuff right down to a very small region, and sort of restricts a lot of models that could sort of deviate from what we might expect from GR. So as a summary, like I said, we observed the center of our Milky Way and discovered a bright ring structure with a diameter of 52 microarcseconds. It turns out this ring structure is consistent with a Kerr black hole that is described, and the plasma around it is well described by a magnetically arrested models that have relatively low inclination angles. Compared with M87, which is 1,000 times more massive, it seems that lens rings appear to be a universal feature of supermassive black holes across the universe. And if we compare the deviations from GR with the LIGO observations, it seems that GR is a strong theory across 10 orders of magnitude in mass. In terms of the future, the EHT is very excited to add new stations. We, of course, added the GLT, which I'm sure everybody here is very excited about, in 2018, and we're analyzing that data as we speak. We also added a new station in Arizona on Kit Peak, and we added the phased Noema array in France in 2021. We increased the bandwidth of our instruments in 2018, and we very much hope that ALMA will approve our proposal to observe at 345 gigahertz next year. And compared to LIGO, I guess EHT sources are very persistent. Whenever LIGO observes an event, they essentially lose a black hole because they're sort of binary operations. But ours will always be there, and we'll always be able to come back and look at it. And so the Sagittarius A results, along with M87 results, represent the first steps in EHT science. And we'll just keep getting better. We'll improve our techniques. We'll be able to help build consistency and be able to make a lot of great observations in the future. Thanks. And of course, here are all the members here at ASIAA that are a part of the Event Horizon Telescope collaboration. And all this work would not be possible without a tremendous amount of work from all these different people. Thank you very much.
Thank you very much, Britt and Cristina, for this very wonderful talk. And many congratulations to the EHT members at the ASIAA and around the world for this great achievement. And now we open for questions. So please use the raise hand function to bring your question. Any questions? Any questions? So Britain, actually, I have one question. So I will look at this the now supermassive black hole image. I was quite interesting, quite curious about this image from the previous one, the M87 ones. We can see a more clear feature of three clumpy, like three knot structures. Yeah, like this one. So I was wondering, what is the physics create these three clumps instead of the previous M87? Maybe two clumps, but
yeah. So the azimuthal brightness variation that you see in Sagittarius A, that's a good question. So in M87's case, because it's sort of static across a night, we can sort of average up all the image and generate the sharp feature. And it turns out from night to night over the course of a week, this brightness asymmetry is very consistent and constant in M87, which indicates to us that this is a relatively static feature. And in M87's case, we associate this with sort of the material coming towards us at the base of the jet. Because of course in M87 we see this very brilliant jet across multiple wavelengths and spanning thousands of kiloparsecs or many kiloparsecs, maybe not thousands, but so we expect this brightness is primarily due to Doppler beaming towards the line of sight, right? So as material is traveling towards us, it'll get brighter, and as it travels away from us, it'll get dimmer, and this sort of gives us an indication of sort of motion in the image. In Sagittarius star, it's a little bit more complicated, primarily from the fact that not all of our methods agree on where these bright regions should live. If we go back up to the image that Cristina showed, you know, amongst all the different methods, these spots kind of live in different places and are sort of brighter or dimmer depending on what method you use. And of course, all of these images are just as good fits to the data. And it turns out that perhaps this is related to different methods sort of weighting data differently at different times. And so this can sort of be thought of as different regions around the black hole sort of becoming you know, more excited at different times. And so we're sort of averaging out different chunks preferentially. But I guess I'll say that the exact orientation and location of these spots is not very strongly constrained. We think they are real, but we don't know, for example, if those will evolve when we take a look at it maybe next year.
Okay.
In fact, we expect them to evolve as we look at it over time.
Okay, thank you very much. We still have time for questions? Any questions? TC, please.
Hello, can you hear me?
Yes.
Great stuff. I was wondering about the future directions that the EHD collaboration is heading. I guess from the press conference, one of the speakers was mentioning about making a movie out of these images. You know, what's your view on this, and you know, when can we expect this to happen?
Yeah, well, to a certain extent, we already have created a movie. Even for M87, we have different images across 4 different days. And so you can think of those as 4 frames of a movie. For Sagittarius star, of course, we again have different images over different days. And even within a day, we can see some sort of small evolution. The problem is for Sagittarius star, because it varies so rapidly, we don't actually get enough coverage to generate a nice looking image on small enough timescales to be able to fit the data well. And so what we're looking forward to, especially with Sagittarius star, is the addition of a bunch of new stations. So for example, in 2018, we added the GLT, which unfortunately maybe won't be able to look at Sagittarius star, but you know, we are adding Noema in France and Kitt Peak in Arizona to add additional stations. And over the future, we're going to add more and more stations across the globe, hopefully, to be able to fill in our UV coverage more and more so that we can separate and sort of chunk out our data into smaller and smaller averaging scales so that we can make movies on shorter time scales. That's the plan, and that's the hope. And of course, you know, you can make a 4-frame movie with M87 already.
Thanks.
Okay. Is there any other questions? Okay, so if not, that's thanks Britt and Cristina again, and thanks everyone for joining this colloquy. Thank you very much. Bye-bye.
Thank you.
Thank you.
Thank you.